And if y'all have any feedback both about the courses or just about how this whole event ran online, we'd really appreciate it because it's kind of a trial run for what we'll end up doing in October at the Real Datathon. But again, thank you all for spending one of your summer Saturdays with us. We really appreciate it.
Allie, are you requesting to share screen? Because I don't think I can give you.
Yeah, so next to the share screen, there should be like a little button that you can hit, allow other people.
Okay. You should have permission
There we
now.
go. Awesome. Cool.
I wanted to let everyone know that this meeting is being recorded. And if you're not comfortable with that, you can just let me know either here or in Slack. And before we post it to the website, we can edit you out. So.
Awesome. Well, I will go ahead and get started with this lesson. We're doing an introduction to NLP. And so I'm going to be going through my Colab the whole time. If y'all want to follow along with me, that's what I sent the link for in the drive, or you can just watch what I'm doing at the moment and then can go back through and look at it yourself later. But as far as an intro, so natural language processing is a field of study that combines both data science, machine learning with human language. It's super new, and there are a lot of aspects of natural language processing that have been developed so far, but there's a lot of areas in which they are still heavily researching and coming up with new things. And so it's a really exciting field of data science. And so some example applications of it are stopping spam emails, identifying fake news, sentiment analysis, chatbots, even translation and spell check. There are so many different ways in which natural language processing is really effective. And as far as what we're going to cover in this course, so it is a crash course, but I wanted to focus on these three main areas. So the first will be text pre-processing, where we'll talk a lot about how to go through your text and make it in such a way that it can be used for modeling. And then we'll talk about feature engineering, which is all about how we can convert text to numbers. And then we will cover some classification, specifically sentiment analysis, using some of the pre-processing and feature engineering steps that we learn. And as far as what packages we are using, there are many NLP packages in Python. But the one I focused on mainly was NLTK, which I believe stands for Natural Language Toolkit. It's a pretty popular one, and it offers a lot of different kinds of tokenizers and pre-processing steps, and so that's why I went with it. And then we're also going to use scikit-learn once we start getting into the modeling section. And if you're following along, go ahead and run this. It basically just imports all the packages into Colab. And if this is your first time using Colab, it's a really handy online version of a Jupyter notebook. So it runs fairly similarly. It's just on Google. Okay, and now for our first section on text pre-processing. So text pre-processing is all about cleaning and preparing human language text. And one of the reasons why it's so important is because it helps you take your raw text and figure out what you actually need to keep in order to model and do insights from it. So it's the trimming down of your text just to keep the most important stuff. And there are a lot of different steps that we're going to cover. They are pretty easy to catch on to, so we're going to talk about all of these. So we'll talk about tokenization, stop words, doing alphanumerics, stemming and limitization, which are similar concepts. Also lowercasing, part of speech named entity recognition, and then a fun little visual using word clouds. And so to start, let's talk about tokenization. So tokenization is the process of splitting up a piece of text into smaller pieces, and there are a lot of different types of tokenization. So definitely the most common way is to do word tokenize, which pretty much just splits text on a space, and so you end up with like a list of your individual words. There's also sentence tokenization, and then there's a regex tokenization. So that's something if you wanted to go in and customize it a little more, maybe you're looking for a specific pattern, that is how you would do that. And then there's also a library that lets you do tweet tokenize. And that one's really interesting if you're analyzing any kind of maybe like texting data as well as tweets, because it's able to pull out like a hashtag and then sentences like that may go together, as if you were doing like word tokenize or sent tokenize instead. It may not recognize some of those things. It also helps with emojis. And so those are kind of the 4 different tokenizers that are built into NLTK. And for what we'll talk about, we'll mostly be using the word tokenize and a little bit of the sent tokenize. And so here's an example in code of what this looks like. So from the NLTK package, we're importing these two functions, the word tokenize and the sent tokenize. And I've gone ahead and I've typed in a little bit of sample text for us. And then it's really just as easy as passing in the text string into the word tokenize function, and the same with the sent tokenize. And so this is the format of what this would look like. And if I run it, you can see that the word tokens are split by word, and then the sentence is split by sentence. Also, if you just blankly use the word tokenize, punctuation marks are counted as a word. So those show up in here as well. And we'll talk about filtering that out in a little bit. That's our basic concept. And this is really important because we'll want to be able to break down large pieces of text into smaller tokens to do our analysis on. And so now moving in to stop words. So stop words are words like a, is, and the that we often want to remove from our text just because they're not going to be super important in predicting anything. They don't have a lot of meaning, but they're found really commonly. And so we're going to talk about how to remove those out of our text. So here's an example of what that would look like. Again, I'm importing the word tokenize, and then you can also import stop words. So it's basically, I believe it's like a list of just stop words that people have defined, and you can update it if you want. So I give an example of doing that as well right here. So if you wanted to take the list of stop words and add some of your own in there, you can do that. A way that this might be helpful is, say, for example, you were doing something on airline data and the word plane kept coming up over and over again. Well, it's probably not going to be super predictive if it's that common. And so in that instance, you could increase like the vocabulary of your stop words to try to filter out some stuff that you're not wanting. So that is an option. But as far as doing this, we start by tokenizing our text again, and then you can do list comprehension. So what this does is it just iterates over your list of tokens, and it says if the token is not one of the stop words, then you're going to keep it. If it is a stop word, you're going to get rid of it. And that's how you filter out your stop words. And so I'll run this here. I show a couple of different ways. So the first one is just the tokens before I do any pre-processing. So before I remove any of the stop words, you can see them here. And then once I take out the stop words, you can see that I think R, N, and A were removed. So those are all in the defined stop word library. And then with the custom one, just for a demo purpose, I took out we. And so you can tell that the we is now gone and this custom stop token. And that is stop words. Do we have any questions in the chat? It looks like some stuff's popping up.
We have two questions. So from John, he's asking, is there an R package equivalent to NLTK that you would recommend?
I actually do not know. I haven't looked into the R side of it. I'm sure they do have something similar, but I can look that up and get back to you on that. I'm sorry, I don't know that.
Okay, and then another question from Shurian. How do we know if a word is a good candidate to be a stop word? Words that repeat a lot and words that add no additional meaning.
Yes, so that is essentially the concept. And so with the stop words library that's been pre-done, words like a, is, and the I mentioned are stop words. So anything that's super, super common is pretty much already in that predefined package. We'll talk a little bit later. There's a model that's called TFIDF that we'll get into in feature engineering. But it basically, if you take a whole piece of text and you see a word is super, super frequent across text, that's kind of an indicator that you don't want to keep it. And in essence, that's how a lot of the stop words were identified, was by taking bulk pieces of text and people saw that they were so frequent that they wanted to discard them. And yeah, if you just think about the English language and like what is found in books, these words, for example, any variation, are, that, all those different kind of words are so frequent, and that's how they ended up determining that they are stop words. So did that answer your question? Is that it, Dan?
Yes, that's it for now.
Awesome. Okay. Well, then moving on after stop words, we are going to talk about alphanumeric filtering. And so there are 3 different functions. These are actually functions just built into the string in Python. And so it's isAlpha, isDigit, and isAlnum. So if you were wanting to only have character tokens, so this would be just words only, then you can do isAlpha. If you're wanting just numbers, then you would use isDigit. And if you're wanting a combination of numbers and digits, then you can use isAlnum. And one of the reasons that we use this is how I mentioned in the word tokenize, you could see that punctuation marks came up as a token, and we may want to filter those out. So a real quick way of doing that is by adding an isAlnum to it. So you can say if this word is not alnum, then we don't want it. So it's a way of discarding different types of tokens. And so here's an example of how this goes. Again, we're going to start just by tokenizing this text. So that's our first step. And then we're going to do this list comprehension filter like I was mentioning. So in this one, I show that you can just take the characters. So what it's doing is saying for each word in tokens, if it's a character word, we're going to add it. Similarly, this one is the same, but for digits. And this last one is for numbers and digits. So if I run it through, so with the character tokens, you can see that even this intro to NLP, because there was a 2 in there, it's taken away, as well as the 25 and exclamation point. So those are not characters and weren't included. The numeric is the only one that's in numeric is 25. This intro to NLP is both character and numeric, so it's not included in here, but it is included in this combination one. So you can see how it ended up parsing the string. So that's how you filter those out. And then also lowercasing. So one of the reasons that this is really important, and it's really helpful when you have strings that have a lot of different variations. So the example I gave here is if you're doing your 2-letter state abbreviation, there are these 3 ways that you can write it. And when you want to very quickly filter through different type of text data, you want them all to be the same. And that just helps for a lot of different analysis. And so one of the reasons that we lowercase is just to standardize all of them. And that way things are grouped together when they should be. And you can do this just through the lower function that's built into a string in Python. And so in here, again, I tokenize first, and then I do list comprehension where I lower each of the characters in tokens. So you can see here that it lowered everything. And again, that's just really helpful when you're trying to trying to reduce the number of words. Okay, and now we're going to move on to stemming and limitization. The 2 concepts are really similar, so that's why I keep grouping them together. But stemming is the process of reducing words to their root form, and what it does is it cuts off the end of a word. So for example, if you have the word stem and the word stems, what stemming does is it's going to take off that S on stems, the plural, so it kind of gets it to its base form. And the whole goal of this is to really make sure that words and all their variations are counted as the same word. This is important when we start getting into feature engineering and such. We want to group those words together so that we don't have too many variables when they have the same meaning. So that's the whole purpose of stemming, and it just cuts off ends. The problem with this is that by cutting off the end, it doesn't always lead to the best result. So for example, here's universe and university. And the way the stemmer works is it's going to cut off the E of universe and the ITY of university and say that they're both this spelling of universe, which those 2 words mean different things. So they probably shouldn't have the same stem. And the spelling of universe actually isn't a real word, so it's not even a valid word. So that example is, I picked it on purpose to show you some of the pitfalls of stemming. In other cases, it does work well, but the goal is just to try to reduce your words to your root form. And there's a function in NLTK called Porter stemmer that we're going to use to do this. So in the example, we start by doing our tokenization again, and then you instantiate your stemmer like this. And what you do in a list comprehension is you invoke that function on each of your tokens. And so it stems them all. And I gave a couple of different examples here so you can see what it does. So test and test should be the same. And in fact, if you see the stemmer, it does reduce both of them down to test. So that works very well on that example. So cacti and cactus, those, one is the plural of the other, and so you would expect that they should have the same stem because they're really the same word. But because of the way it cuts off the endings, it's saying that they have different stems, so it doesn't group them together effectively. And then here's that universe and university example again. So that's showing that these are two words that shouldn't have the same stem that do. So those examples in the text just kind of show you the different ways in which sometimes it works well and sometimes it doesn't. And Dan, did we have any questions pop up in the chat?
Yeah, we have one about the previous slide. So John is
Okay.
asking, what should you do when you have an abbreviation that is another word when lowercase? So the capital THE is also an abbreviation for Times Higher Education.
Oh, yeah, that's a good example. I think as far as lowercasing goes, it really depends on the context of what your text is in the first place. And so if there's something like that that you know could be an issue, then maybe that's not the best idea to go ahead and lowercase. Especially like people probably, I guess there could be instances where they would capitalize the word the completely, maybe not. So yeah, I think that is something that you would definitely, you may have to go kind of through by hand and identify those cases. Also, it would be nice if abbreviations, if they would like have the dots in between so you know what it stands for, but people don't always feed in data that is good to manipulate. So that's part of the fun as a data scientist, is getting to go and fix that. But I think that was a really good example that you brought up.
Okay, that's all the questions we had.
Okay, awesome. So then limitization is super similar to stemming. It's the same concept. It's wanting to reduce words to their root, but instead of just chopping off the endings, it actually references a pre-built dictionary of lemmas. And so it's something that people have made and actually identified what the actual word should be. So it's a little bit slower than stemming, which is why stemming is sometimes used. And it's slower because it's having to reference the dictionary instead of just looking at each word and cutting off the ending. But one of the good things about lemmas is they are always a valid word. When they're produced, you don't have any of the case like universe earlier where it's not actually a real word. It does reduce it to a word that is in the dictionary. So here's an example. It does something similar. So studies becomes study. And this is something that wouldn't have happened with stemming because there's no Y in studies. So it wouldn't have ever reduced it down to that point, but the lemma can find it because it's been pre-built. And so the way to do this with NLTK is this word net limitizer. And so here's the same string that we passed into the stemming, but now we're going to do the limitization version. And as far as running it, it's the same. You instantiate it and then you invoke it. And so you can see here again, tests and tests become the same like it did in stemming, like it did in stemming. Cacti and cactus in the other version, they didn't reduce to the same one, and they do here. And universe and university are kept as their word because you can't deduct them anymore and have a valid word. So with this string, limitization definitely worked better than stemming did. All right, now we're going to move on to part of speech tagging. So what this does is, given a text, it can assign what part of speech each token is. And we're going to use this using the pause tag function of NLTK. And so here you import it, and we go ahead and we tokenize our text, and then you just run the function on your tokens, and it prints them out. So I can show you what it does. So some of these abbreviations, if you don't know them, like I didn't know what some of these meant, but if you look them up, they tell you what part of speech it is. But so cow is a noun, jump was a verb. So you can, it does pretty well in identifying what each word is. And one of the reasons that we want to use this is A, for context. That helps when you're doing any type of modeling. You can tell like how a word is being used. That could be a good feature. And then it also leads us into this named entity recognition, which starts off almost the exact same way. But it takes it one step further. And so named entity recognition, after you identify the parts of speech, the ones that are nouns, it goes through and it tells whether or not it is a named entity. So like a place, a person, an organization. And so it's really just saying it's not just a noun, but it's a named entity. And we do this by adding the any chunk function after we've done our part of speech tagging. And so here starts off the same. You tokenize, you run part of speech, and then we just run this any chunk. And the output of that function is a little weird. So here, this just prints it out in a format that's easy for y'all to see. But so nouns in this sentence would have been Eiffel Tower and Paris, and it's grouping them together. So it knows that Eiffel Tower, it wouldn't have them as two different named entities, but it actually put them together as one. So it does that step for you too, which is kind of cool. But it correctly is able to identify what the named entities are. And now for some fun viz. So we're going to talk about building word clouds, which if you haven't seen a word cloud before, what it does is it takes all of the words in the text and then it bolds and makes really big the ones that are frequent. And so you do this with, there's actually a library, a word cloud library that we are going to use to build one of these. And you can also filter out stop words with this as well. It has a built-in stop words too if you're wanting to. So my example text is the subway catchphrase. And what you do is you instantiate a word cloud. You can customize it so you can change the background color. You can put stop words if you want it, but you instantiate it and then you generate it or fit it on your text. And then you can show it through Matplotlib. So for example, here's this one, show you what they look like. And any was cut off because of the stop word, so it doesn't pop up here. And I think every time you run it, it like generates a different picture. So it's kind of fun to play with and see what you get. So that's the essence of word clouds. It's not really a pre-processing step per se, but if you're wanting just to get a feel for your text, it's just a good way to kind of have a viz before you start going anywhere further. So that completes our text pre-processing section. I have some practice problems for y'all. If you are wanting to do practice on your own, we're not going to go over them, but there's a file in that drive that's a Harry Potter text file. And so you can go through and has each of the steps that we talked about mostly filled in. I left like blanks where you would go and input the function that you should run. So that's a good way to practice. And do I see any questions, Dan?
Yes, Shurian is asking if you might be covering this later on, but can you give a quick example of all of these techniques you just covered working together, like a practical application?
All of them in one. So the biggest application of doing all of this is when you're putting stuff in to features and modeling, and you don't necessarily use all of them at the same time. It kind of depends on what text you're wanting to do. The practice is actually a pretty good example of that because I throw everything together on one text. So it starts by loading this Harry Potter text file, and then it goes through each of the steps in sequential order. So your output will be after you've done all of the steps. So that would be a good practice if you're wanting to use that.
That's all the questions we had.
All right, okay. Well then on to our next section, which is feature engineering. And this one is really important. It's kind of the whole crux of what natural language processing is for. But so feature engineering is a term that's used all across machine learning. It's not just text specific, but it's this process of transforming data into features that you can use for modeling. And it's important because machine learning models have to have numerical features. They can't run on any kind of text. And so we're going to talk about some different ways that we can convert our text into numerical features. We're going to start off with some basic features, and I'll explain what that means in just a few seconds. And then we'll get into some more complicated things like bag of words, TFIDF, and a little bit of word embeddings too. So as far as some basic features, these are things that aren't too complicated to calculate, but they could actually be pretty helpful. So we can go through and we can find the number of characters, words, or sentences. You can take it a step further and do like average word, sentence, and paragraph length. And you could also find number of capitals and punctuation marks. There's a lot of other things that could be really similar to this. These are just a few examples I thought of. And these may be useful for, first of all, text readability. So there's a branch of natural language processing that looks at text and it tries to figure out what the level of understanding would be to read that text. So for instance, if you're putting together a presentation or if people are doing legal documents and they want to make sure that their clients could actually understand what they're communicating, that would be a way. And why these features are helpful to that is, for example, if something is really complicated, it's a complicated piece of text, then it probably has a lot of words or really long words, that kind of thing. So those features could help in identifying the difficulty of your text. And then towards the latter, the number of capitals and punctuation marks, those could be good features to use in sentiment analysis. For example, if someone's really passionate about something, they may write in a lot of capital letters or they may add a lot of punctuation marks. And so those could be just little things that you would want to trickle into your model. So we're going to go through a couple of examples of these, not all of them, but as far as finding the number of words, so again, we will start off by tokenizing. And then here I did the word tokenizing again. And then you can iterate and you can just find the length of your sentence for all the sentences. So it'll tell you how many words you have in each sentence. And so if you think about this, this is obviously not in a data frame format, but it's very similar. You would just end up pinning this like as a column, and that would be a feature that you could use. And then if we want to find the average length of words, it starts out the same. So you build your tokens, but then what you do is you find the length of each individual word, not the length of your sentence. So it calculates each word's length in characters. And then if you take like the sum of all of those divided by the number of words in the sentence, you get your average word length. And so that's how this works. And so you can see in this first sentence and the second sentence are the same, and it comes out that way, as well as in these two, you can see what that is. And so those are just two of the basic examples I wanted to show. Like I said, there's a lot of different ones you could play around with, and I have practice problems at the bottom that go through a couple of the different ones. And so now on to bag of words. These next three different types of feature engineering methods I'm going to talk about are really concerned with trying to get as much information from a piece of text as you can. With the earlier two, we were pretty much just getting a metric, right? So getting a length or an average length, and so you're not keeping any information about the words themselves other than how long they are. But the problem is, like, our text features are so rich in what they contain and in terms of what the words mean and how they're placed together, and we want to keep as much of that as we can when we're transforming it into a number. And so that's what we're going to try to do here with bag of words. So there's a concept called one-hot encoding, which is used in machine learning. What it does is if you have a categorical column, it ends up splitting it into a structure like this. So each category would become its own row, and the values are binary indicator values, a 0 if the word isn't in the row, and a 1 if it is. And so this is a way that people are able to take categorical data and turn it into numerics. And bag of words is really similar to this. And instead of having just one word like mun, you would have a whole sentence. And so it's doing that same concept just on more data. So bag of words, like I was saying, it goes through and it calculates your vocabulary. So it would look at all your text and it would find every word that was mentioned in all of your examples, and those would become your vocabulary or your columns that it's then going to do a binary value on. So it goes through and it can tell you how frequent that word is in each row. And so this is the whole bag of words example. You can kind of see what your output would look like here. Now, something to think about is if you have a lot of words, you are quickly going to have a lot of columns, and that's not always a great thing when you're doing any kind of modeling. You want to try to find this balance between like not having too many and overfitting, but also having enough that things are important. And so that's kind of a theme as we talk about all the rest of this, is finding that perfect size. And there's something that we can do that we learned about in the last section. So preprocessing text does help with this. So if we remove the stop words, if we limitize, if we get rid of punctuation, all of those things will help get rid of some columns automatically that we know we don't really need. And so that's why that whole first section was so important. And so as far as implementing bag of words, we're going to now use sklearn's functions. So there's a count vectorizer for us, and it actually has some nice built-in pre-processing steps. So you can add in the parameters like lowercase, strip accents, stop words. This token pattern, if you didn't want to use word, it's like tokenization basically. So if you didn't want to use word tokens, you could throw in your own regex pattern there. So those are all different pre-processing steps, you can do. And then there's a couple other features that we can use in it that help with us figuring out what the size of our data frame should be. So max features is pretty explanatory. You can cap off the number of columns or the number of features you want to include. So you can throw that in there. Then there's also max and min DF, which DF here stands for document frequency. And so that's just how common that word is across all of your texts. And so if a word is super common, like we talked about earlier, and you don't want to include it, kind of like with stop words, then you can set that max DF parameter. So if a word is more common than whatever you set, it'll not include it. Similarly with the min DF, if a word is too infrequent, then it may also not be very effective. And so you can put that parameter in too. And then there's n-gram range, which I wanted to describe a little more, so that's why there's a picture here. But an n-gram range really helps you provide context, because bag of words in and of itself just has one word, like you would see here. And in this example, happy not sad and sad not happy, those mean completely different things, but they would have the same bag of words because you don't have any idea of where the words are positioned, and that changes meaning. And so what n-grams are they are groups of words that are consecutive. And so, for example, here, this would be a bigram because I'm just doing 2 consecutive words. And if you add those as features, it helps a little more with that word context. And so it's something else that you can play with and pass in. But again, there's this whole battle of how many consecutive tokens should we include? Because if you include, say, like maybe 10 consecutive tokens, then the dimensionality gets really big, and the likelihood that you're going to have the same 10 tokens in a row on multiple things of text is really low. So it's probably not going to be useful. So all of these are different ways that we're kind of trying to do the same thing, which is finding your best features while not overfitting. And I know that was a lot, but now that you know a little bit about bag of words, now we're going to show you how you would implement it. So from sklearn, you can import this count vectorizer, and then I go ahead and I make this text into a series, just so we're getting a little more into what modeling would look like. And then you can instantiate the count vectorizer, and I go ahead and I'm passing in the English stop words here. And just for our first example, I'm actually gonna just take this out. So it'll default to just one word only. And then you can fit it and transform it. Fitting it just creates that vocabulary that we were talking about, and then transforming it turns it into the matrix. So those are 2 different steps. You could actually write that in 2 different functions. You could do vec.fit and then vec.transform, or there's this combination one. And then the output of this is a very sparse matrix, and so in order to visualize it, you actually have to turn it into an array. And then to get the column names back, or the feature names, you put this function in. So this is just a way to visualize it after it's done. And if I run it here, you can see it took out the stop word, so there's no the and n, and this is what it would look like. So it goes through, and so this one is cat sat, so you can see cat sat. It does it for that. And then if you just wanted to see what some of the other parameters do, here's that n-gram range one. So here I'm saying that we'll have 1 word vectors and 2 word vectors. And so now like cat hat is added, cat sat is added. So that just expanded our data frame there. All right, and then one of the shortcomings of bag of words is that you can try to fix this with the whole max df, min df arguments, but there's a model that actually expands on wanting to reduce words that are frequent across lots of different texts. And so that's what this TFIDF comes from. So term frequency, which is the TF part, is the number of times a word appears in one text. So it's a proportion of times. So it's basically what bag of words is doing. It counts how often it appears in an individual piece of text. But then this model combines it with inverse document frequency. And so document frequency is the proportion of times it appears across all of the text, not just the row you're looking at. And so this model combines this notion of wanting to count how common it is in your specific document and then deduct if it's common across everything. And so this is what TFIDF is. So here's the formula for it. If you're interested, it's basically just term frequency right here, and then it's the log of your inverse document frequency. And so in this example, instead of it being counts, now it's not an integer necessarily, it's this score, this weight that the model produces. And so you can kind of see how that would end up being here. And it's super similar to bag of words in terms of how you implement it. You just switch out, instead of count vectorizer, you use TFIDF vectorizer, and it has the same pre-processing steps, the same parameters you can tune. So literally the only thing in terms of implementation that's different is the name. And just showing you they're the same. To notice it's just this that's different, and here as well, but it'll look similar. And now instead of it being counts, you have your weights. And so this is just a different way of trying to score the importance of your words. And we're going to touch on word embeddings briefly. This is a more advanced concept, but it's important. So I wanted just to kind of give a quick overview of what this is. But one of the things that the bag of words and the TF-IDF models don't do very well is compare similar words. So it's able to show you like the frequency of the words, but not how they relate to each other. And so this whole word embedding concept is really trying to give you a vector that you're able to compare if words are similar or not. And it's calculated through neural networks, so it gets a little complicated. But here, the way neural networks work is it goes through a process of creating features by passing it through a bunch of iterations. And so the features aren't named necessarily. So this is just for me to illustrate to you. If your words were king, queen, prince, and princess, maybe it measures on features like royalty, masculinity, and age. And so they're all royal, so it would be able to say that, versus king and prince are masculine and queen and princess aren't. And it does age. So it would go through with each word, and it creates a list of different weights across whatever features it ends up measuring on. And in this way, you can compare two words directly and see how similar they are based on all their scores on those different metrics. And so it's kind of what word embeddings do. And this just adds a whole extra layer of being able to tell if things are similar or not. And as far as implementing it, we're going to use this library called Gensum, and it's called word2vec. And there's a couple of parameters you can tune. So size is the number of like things you want to iterate on, so part of the neural network process. Window is how closely related two things should be. Min count, so if something isn't very frequent, that's what you would set it to, so you can say how common something has to be in order to use it. And then workers is also part of the building the model. How many different workers do you want building it at once? And as far as implementing it goes, NLTK also has a lot of text that you can download straight from it. They have saved through the library, and so I'm doing that here. I'm just downloading. This is a bit of Alice in Wonderland is what this is. And then we tokenize it, and I added some pre-processing steps in here too. So I lowercase, and then I only include characters, so I'm getting rid of punctuation. And then what you do for word2vec is you pass in those tokens, and I put a couple of parameters in here, and it's able to create the model. And there are two different functions I wanted to show you here. So this one, that's just similarity. If you pass in two words that were in your text, it can give you a percentage value for how similar they are. Versus if you do this most similar and pass in one word, it'll pull up the similar, like I think it's the top 10 similar words defaulted to that based on what the model finds. And so here, for example, Alice and her were pretty similar. They must have been used a lot in the same context. And then as far as red goes, it pulls up angrily, turn, poison, chapter. So those are some of the words that it found that it was similar to that. And I know that was a really quick introduction to Word2Vec. That whole aspect of natural language processing goes way deeper, but I just wanted to mention it so you knew it was out there, that you could find similarity between words. And then there's practice problems for that as well. And I know I'm starting to run a little bit low on time, but hopefully we'll get into some of this classification. So specifically, I wanted to talk about sentiment.
We have about 5 minutes left. And then I wanted to let everyone know that I'll be sending a link in the chat for a survey, and this will help us get your feedback. It should only take about 3 minutes. And then after you guys fill out the survey, we'll open up for a Q&A.
Awesome. Thanks, Dan. Okay, so sentiment analysis is when you're wanting to figure out what opinions people have. Traditionally, it's positive, negative, though sometimes you have neutral, or you can find different types of emotions too. And there's two different ways that people go about this. So one is rule-based. For example, maybe the word good has a score of +3 because it's known to be positive, and bad would be -3. So rule-based has these assigned values, and it goes through a sentence and it adds up all those different values and it'll come out with a score. And so if it's positive, then you would say positive, and if it's negative, you'd say negative. So that's what a rule-based approach to this is. Though as we mentioned beforehand, the context makes a big difference in determining meaning of a sentence, and so rule-based doesn't really get you that context because it's just looking at the word individually. And there's also the machine learning approach, which I'm going to talk about briefly here. And it gets into supervised learning is what we're going to cover, which if you're not familiar with supervised learning, we have a course on machine learning that y'all should take. But just as an overview, what it is if you have a data with known outcomes, you can train a model on it and then use it to fit on data that you don't know the outcome for. And so some of the things that you have to do here are test, train, split. And so that's when you split your data into stuff that you're testing and training on, and then you fit the model and then you look at how well it does. And so classification, which is what sentiment analysis is the task of predicting a class or a category based on your data. And this can either be binary. So in the case of positive, negative, it would be binary, or it could be multi-class if you had more than 2 things that you were trying to predict. And there are lots of models that are used in classification. I'm going to use this logistic regression in our example here today. But what it does is it creates this curve, and there's a threshold value. So if you're looking at this picture of the curve, maybe the threshold is right here in the middle where I'm kind of drawing my cursor. But the idea is if you're below that threshold, we're going to classify it as a 0. If you're above it, we're going to classify it as a 1, or positive, negative if you're thinking sentiment. And so that's what logistic regression does, not getting into the math behind it, but it just creates that curve where it'll classify your sentiment. And so what you can do, and I'll do, so there's a file that's in the drive that y'all can upload and run. But if you run it and load it in, it's the IMDb sentiment, so it's movie reviews. And then we're going to take our features, so we're going to say X is the review, the text review, and Y is the sentiment. And then import all of these packages that you're needing. Then you would do train, test, split on your data. And then we're going to build a count vectorizer, so the bag of words. And then once you have the bag of words, you're going to fit transform it to your training data. And then here's a difference I wanted to point out. So before, when we were doing bag of words, we did fit transform all the time. But what the fit does, like I mentioned, is it creates that vocabulary. And so when you have a training and testing data, it's likely that in your testing data, there are words that probably weren't used in your training data, which would throw things off. So you actually only fit it to your training data, and then you just apply whatever was created to your testing data, and that prevents like unknown words from throwing things off. So that's why those are a little bit different here. So up to this point, you've just created your bag of words model on your features. And then what you do is you can instantiate your classifier and fit it on your data. and then you can make predictions. So if you do that, no, I haven't run this one. Great, it's in here. Okay, let me run it for you. And actually, even though we didn't do much and there's hardly any pre-processing in here, it ends up predicting pretty well, which is exciting. It has 0.86 accuracy. And so this was just us doing a bag of words. So just counting the frequency of words, we were able to predict the sentiment with 86% accuracy. And if you do a confusion matrix, you can also see how often you were misclassifying things. And so I know that was a really quick intro into classification, and I'm sorry that we didn't have a lot more time to go into it. Again, if you want to take a look at this notebook, I have some other examples. Another common model that people use is naive Bayes, which is just based on Bayes' theorem. In terms of how you run it, it's really similar. And you can interchange the count and the TFIDF vectors if you want to mix that up a little bit. You can change your models in order to really try to figure out what the best model would be. And there's also the whole aspect of parameter tuning as well. So that's where this whole machine learning gets really interesting, is because there's lots of different things that you can customize in order to figure out what works best. But if you want to take a look at this, I have the naive Bayes and TF-IDF example. And then in the practice problems, there's the other combinations of those two. So you can compare all 4 of those different models and see what ends up working the best on that data set. And since we're almost out of time, I want to go ahead and open it up for Q&A.
Okay. Hey, everyone. I just sent a link for a type form in the chat. So if you could take a few minutes to click on that link and fill out that form to give us feedback on this event, that would be great. And then after you're done filling out the form, feel free to type in questions in this chat for Allyson, or feel free to unmute yourself and ask questions. Looks like there aren't many questions. Okay, so we have one question. What do you use the classification models that you were talking about for?
There's a lot of applications for classification with text. So one of the examples I was talking about specifically was sentiment analysis. So if you wanted to say if someone was positive or negative, like with their review, that's one area that's really popular. There's some other different examples of classification too. So thinking movie-wise, again, you can go through and look at maybe movie descriptions, and you could say what type of movie it was. So all of those are 2 different examples of classification with natural language processing. Another big area of machine learning with NLP would be like recommendation engines. So again, if you're thinking movies and you want to look at descriptions, you could be able to tell what things are similar. So that's, if you were classifying it, then that would be a way that just really leads into recommendations too. Those are just a few ways. And where can you look for resources? I am actually about to compile a list of all the things that I looked at when I was preparing for this lecture, so I can put all of those in something and upload it. The recording to this lecture and my collab and the text files that are uploaded, those will all be on the TAMU-Dathon website a little bit after these lectures. So if you want to go there, I'll also put in some resources there for you to look at.
And also, do you have any beginner level NLP projects that you would suggest working on?
Yeah, so some beginner level ones, any type of classification is a pretty beginner NLP thing. So like I did with the model that I put in the collab. So that was something that I took straight off of Kaggle, the movie set. So there's a lot on Kaggle. If you go and look, you can do any type of classification, would be a good way to start. And like you saw, we just did a very basic count vectorizer function and it predicted with 87% accuracy. There are probably plenty of tweaks that you can make if you spent some time messing around with different parameters that could get you up into that 90 range. So I think those would be really great projects to try out. Another fun thing that people like to do is try to build a chatbot. It's a little bit different than what we covered here, but I think between recommendations and sentiment analysis, those would be really good beginner problems to tackle. And then you ask if you can use NLP for finding a specific pattern of the DNA. Ooh, that's a really interesting application. I know like biostatistics is really popular nowadays. That might be something that they're doing there. But I think if it's something text-based, that could even be something that's more like regular expression-wise that you could go and you could parse and maybe figure out what different pieces were incorporated. Yeah, I think that would be a really cool thing to look into. Awesome. Were there any other questions?
Thank you for the great introduction.
Well, thank you so much. I appreciate all of y'all hopping on. This is a really fun first event we're putting on. And so if you'll go ahead and fill out the survey, that'd be great so we can know what to do better next time. And then if you're interested in taking any of the other courses, go back onto the events page and go to those. And you should also apply to TAMI DataFund in October. So, yeah. All right, if there are no other questions, then we can go ahead and end the meeting and we'll see y'all next time.